In this recording, we're going to learn about polynomial identities. As it says here in the first paragraph, polynomials are just expressions of addition and subtraction of variables and coefficients, all raised to non-negative integer powers. Okay, so the exponent has to be a whole number, right? Like 0, 1, 2, 3, 4, 5. And we can have single variables or multiple variables. So based on that definition, which is not a polynomial expression, I'll give you a chance to examine these four choices and then play the recording when you're ready. Okay, so hopefully you considered those and you saw that each one of these, 1, 2, and 4, have exponents that are non-negative, okay, as it says here, and integer powers. But this one has a negative. It also has a non-integer here. So choice 3 cannot be. The exponents must be non-negative integer powers. So what are we going to do with this? Well, as it says here, polynomials consist of basic operations that can be manipulated using associative. You can change the grouping of the terms, commutative law, which means you can change the order of the terms when we add or multiply, and then distributive property. Well, we're familiar with the distributive property, right? And so based on that, we can use those operations to create what's called identities. And identities are equations, as it says here, that are true for all values of the replacement variable or variable. So a real simple example of this would be the identity x plus 0 equals x. Okay, so for any value that you can think of, this is going to be a true statement. All right? This is a common identity, x squared minus y squared. This is a special difference of two squares pattern that we know well. So we're going to test it out. We're going to test it by using actual values of x and y. And then we're going to prove it by manipulating it algebraically. So what I'd like you to do is sub in x equals 10 and y equals 3. Sub it into the left side, sub it into the right side, and show that it really works on both sides. Because hopefully you took the time to do that. We'll work that out quickly. Okay, so we've shown here that it works for this particular pair of numbers. That's cool, but if I want it to work for all values of the replacement variable or variables, I need to do so algebraically. I can't just show it with two randomly chosen numbers. So what we're going to do is leave the left side alone. Okay, so we'll write out the left side. We'll just do some algebraic work to the right side until it looks like the left side. Okay, so we'll distribute it out. Feel free to use the box. Notice I'm going to leave the left side alone. You can use the box method for multiplying these binomials if you like. Okay, so these are opposites. And I just draw an arrow down to show that that all stayed the same. This changed. Alright, so now I'm going to use this identity to do something. I'm going to find a difference, 50 squared minus 49 squared. Well, in this case, I'm going to let x take on the value of 50 and y take on the value of 49. Okay, and at this point, I can just make my substitutions and work out. Okay, so the advantage of doing this is I don't really know what 50 squared minus 49 squared is, because I don't know what 49 squared is, and that'd be complicated. But hey, I do know 50 minus 49, that's simple stuff. And I can certainly do 50 plus 49, that's 99. Alright, and so the difference between the squares of those two numbers is just 99, and that's pretty powerful. Okay, that just comes down. So now I'm going to use this identity to simplify and evaluate this product. Again, this would be a hard one for me to do in my head, but if I recognize that, okay, 51 is 1 away from 50 and 49 is 1 below 50, I can make some assignments here. I can say, okay, that's kind of like adding 1 and subtracting 1 from 50. So I'm going to let x equal 50 in this case, and y equals 1. All right? And so the 50 squared minus 1 squared is what x minus y would be, right? Now on the left-hand side I can do 50 minus 1 and 50 plus 1. That'd give me the 49 and the 50. 51, excuse me. Now the right-hand side I'm not going to touch because that is stuff I'm not sure about. I'm not sure what 49 times 51 is. But the left side looks pretty easy to me because I can square 5 pretty easily. That's 25. And therefore the square of 50 is 2500. And then just minus 1. So 2499 is got to be equal to 51 times 49. Pretty cool. Alright, now it asks me to prove this identity, but by that it means show that both sides are equal using algebra, and then use it to evaluate this particular number 35 squared. Alright, so let's work that out. On the left side I want you to multiply a plus b times a plus b. Remember, don't just square terms. That's what inexperienced algebra students do, not you guys. And show that it works out to be the right side. So let's leave the right side alone, and let's work out the left side. So play this recording when you've worked this out as far as you can. We'll just leave the right side alone. Okay, so hopefully you took the time to do so. Okay, that all works. Now, to make a 35 squared, I've got to think about what I want a and b to be. They can be any two numbers that add up to 35, but let's choose 30 and 5. Okay, so at this point, I'm not going to do too much with the left side, right? Because I don't know what 35 squared is, but I'm just going to say, okay, that's going to be 30 plus 5 squared, which I don't really know, but I feel like I could work out the other stuff. I feel like I could do 30 squared, and I certainly could multiply 2 times 30 times 5, and I could certainly add in 5 squared. And if you're saying, where are you getting these numbers? Think about it. Here's our identity, a squared plus 2ab plus b squared. And I've defined what a and b are, so I'm just making substitutions into the right side of the identity. Well, I'm going to leave that left side alone, but the right side I can work out. And you could check that with your calculator. Thanks for watching.